Now let's talk about results. A big question when you're looking at the results of a trial is to think about whether or not there is significance, clinical or statistical. Now, having a statistical difference does not mean that it's clinically important. There are some trials that may show that you have a 1-point reduction in a 100-point scale that absolutely means nothing to clinical, like as a clinician. But it is statistically significant. Don't be caught off guard by that. Or don't fall into that trap. Statistical difference simply means that the p-value is less than 0.5 or that the confidence interval does not cross 1 or 0, depending on the type of trial. Clinical significance, however, means that the extent of change is that it makes a real difference to subjects' lives, how long of the effect, and the customer acceptability, cost effectiveness, and ease of implementation, meaning that it means something to your patients. Now, I do not expect you guys to know those differences just by looking at them because you guys have not had that clinical experience. But it is something that I want you to start thinking about. Is a reduction in blood pressure of 2 millimeters of mercury actually clinically significant to your patient, even if it does show that the p-value is less than 0.05? Don't get caught up into that. The next thing I want to talk to you guys about is how to measure the benefit versus risk of a trial drug. And part of that we can do is actually calculating the number needed to treat, or the number needed to harm. Now, to calculate number needed to treat, you first need to calculate the absolute risk reduction, which is that where you subtract the risk of the outcome in the control group minus the risk of the outcome in the treatment group. This is also known as the absolute risk difference. If this equals 0, it means that there is no effect. And this gives us an indication of the baseline risk of treatment effects. Now, we can use this to calculate the number needed to treat, meaning how we can prevent one outcome or improve one outcome based off of how we can prevent or use based on the number of patients we have to treat with the drug. Number needed to harm, on the other hand, will do the exact opposite. How many patients you need to harm. And it actually uses what is known as the actual reduction or attributed risk. It's calculated the same way as absolute risk reduction, it's just using side effects. So let me give you an example of how to calculate number needed to treat. This is actually a non-inferiority trial. What you're going to see here is that there are some times that you cannot calculate your number needed to treat. One thing you need to keep in mind is that we only calculate number needed to treat on nominal data that, or also known as non-continuous data, showed a significant difference and also met superiority. So, you'll see here that the p-value for non-inferiority here is less than 0.05, but did not meet superiority. So we cannot calculate it on this one. If this was something like blood pressure readings or height or weight, that is considered a continuous data point, we also couldn't calculate it then. But we can calculate it whenever it is a significant difference and it meets superiority. So what you'll do here is you will take the absolute risk reduction, which is this number minus this number, as mentioned before. Now you can either convert it into its decimal form, so that would be 0.121 versus minus 0.105. Okay, so that would give you your absolute risk reduction. What you probably got there was 0.015. Now, If we take 1 over the absolute risk reduction, that gives us our number needed to treat, which equals 66.66666. Now, one thing we need to remember is that you cannot have a 0.6 of a patient. So for that reason, we're going to have to do some rounding. For number needed to treat, we always round up. So this would be 67. And the reason we always round up is because we never give the drug the benefit of the doubt. So if we're trying to state that it's going to be doing something good for the patient, if I were to round this down to 66, that would mean that there was one less patient that needed to be treated with the drug before they would get a better outcome. So that's giving the drug the benefit of the doubt. That means that there's one less patient. Versus, if I round up, that means that it's being more conservative and saying that you need to treat one more patient before that. So, always round up on number needed to treat. For number needed to harm, you always round down. So, giving you another example of a number needed to harm, let's just do this one right here. So first we're going to calculate our attributable risk, which equals the controlled events minus your experimental events. So that's going to give you 1.5% difference, right? So that equals 1.5%. Now you want to change that into a percentage, so to 0.015. And then if you do the 1 over that attributable risk, that's what gives you your number needed to harm. So, lucky for you guys, 1 divided by 1.015, we've already calculated, equals 66.6. For number needed to harm, we always round down because, again, we want to assume that it takes one less patients. We never give the drug the benefit of the doubt to have this event. So 66 is our number needed to harm. Again, some rules of thumb. 1, you can only use nominal values. Continuous variables like blood pressure are not appropriate. You only do it if you have a significant difference between groups. Non-inferiority does not count. And finally, you always round up for number needed to treat and down for number needed to harm. When you're evaluating your results, you do want to start asking yourself these questions. Is there a statistically significant difference between groups? Is there a clinical significance between groups? And then can I calculate a number needed to treat or a number needed to harm? When you're looking at this, you're going to have to figure out clinical significance based off of your clinical experience. Statistical difference is pretty easy to figure out. It's either going to cross the confidence interval as stated, or it's going to have a p-value of less than 0.05. Number needed to treat, number needed to harm is a little bit tricky. You have to think about the overall risk or the overall treatment or versus harm for each of these things. There are certain trials, like cardiovascular trials, where you will see that patients, you need to treat hundreds of patients before you have one good event. But the event that they're talking about is usually something really, really bad that happens, like an MI or a stroke. Versus for the number needed to treat for smaller trials or trials that, the difference may be a lot more of a higher magnitude, but of lower overall effect. So like C. diff trials, I've seen C. diff trials where the number needed to treat is like 2. It's going to be dependent on your clinical knowledge, and it's going to be dependent on the overall types of outcomes. All this is found in the results section.